Hello and welcome to another video, again still on trigonometry. Much like chapter 9, however this is chapter 10, which is Trigonometric Identities and Equations. So what I would suggest strongly that you are doing is being completely comfortable with chapter 9 before attempting chapter 10 here, because chapter 10 links directly to the content covered in chapter 9. So we're going to have a look at how trigonometry can help us form identities and equations which we can then solve using this knowledge. So before we begin proper, there are some warm-up questions, so here they are. Now these warm-ups seem very simple, and they are in a sense, but the point of these warm-ups isn't really to brush up on your GCSE trigonometry so much, it's to see if you can spot a pattern between the angle here and the coordinates of B, which are x and y. So have a go at these and be bearing in mind that there is a pattern to be discovered. I'll explain the pattern to you anyway, but it will be more powerful if you can see and hope to find this yourselves. So without further ado, let's have a look at question 1. So as it says, for each of these questions, use trigonometry or otherwise. I just say use trigonometry, don't worry about the otherwise part. We're going to find the coordinates of the point B below. So what I'm going to do first of all is just label on the diagram what we're trying to find. So we want to find x and y, and so x is going to be the length of this line OA, and the y coordinate is going to be the length of this line from A up to B. It doesn't matter if you find x or y first, it doesn't particularly matter. What I'd suggest doing, to be honest, is finding x first and then finding y. As I say, not that it matters. So if we're trying to find x using basic trigonometry for right-angled triangles, we're wanting to find x, which is the adjacent side, and we know the hypotenuse, which is 1. So if we're interested in the hypotenuse and the adjacent, that's going to be the cosine function. So cos 30 is the adjacent side, which is x, divided by the hypotenuse, which is 1. Because we're dividing by 1, we can see here that therefore x is just going to be cos 30. So x is just going to be cos 30, and at this stage I can forgive you if you're not sure what cos 30 is. Cos 30 is a special ratio which we'll talk through in future lessons. So cos 30 is going to give us a value of √3/2. In a similar way, sine 30 is the opposite divided by the hypotenuse of a triangle. The opposite side here is y, and the hypotenuse again is 1. So because we're dividing by 1, obviously y is just going to be sine 30. 30 is a special angle, so sine and cos 30, the values of those should be remembered. But for now, use your calculator if you'd like. You always can, of course. Sine 30 is just going to be 1/2. So for this one, B is just simply √3/2 for x and 1/2 for y. Now again, I did mention earlier to just see if you can try and spot a pattern going on here. So √3/2 was the x coordinate, that linked to the cosine of this angle here, and 1/2, which was y, related to the sine of this angle here. So let's see now for questions 2, 3 and 4 how cosine and sine relates to this angle here. So far, cosine relates to the x-coordinate, y is given us the y-coordinate when the distance of the point from the origin is 1. Question 2, again, the distance of B from the origin is still 1, only here now we have an angle of 120 degrees, and again you'll see here, like question 1, this is measured from the positive x-axis anti-clockwise until we get to the line OB. Now using basic trig, what we try and do here is work out an acute angle we can work with. So if this is 120, angles on a straight line out up to 180, this here must be 60, which we can now work with. In this case, however, OA is going to give us a negative value because this is in the negative section of the x-axis. The point where y is over here, that's still going to be positive. But here I'm just going to call this side OA and this side AB to avoid any confusion with positives and negatives. So first of all, we can think about what OA is. And so the length OA is the adjacent side, and we know the hypotenuse is 1. So it's going to be the cosine function again, cos. So for this triangle here, cos 60 is going to be the adjacent side, which is OA, divided by the hypotenuse, which is 1. So therefore, the length OA is simply going to be cos of 60. And again, feel free to use your calculator to work this one out. So cos 60 gives us a value of 1/2. So this length is 1/2. That tells us that this value here, where A is, will actually be negative 1/2. The size of OA is 1/2. The actual A, though, is -1/2. So there's a difference between the magnitude and the value. Magnitude is always positive. This value here, though, of A happens to be a negative because it's in the negative portion of the x-axis. We can now work out AB by taking sine of 60. Sine of 60 is the opposite side, which is AB, divided by the hypotenuse, which once again is just 1. Therefore, AB will just be the sine of 60, which we can work out with a calculator once again. So sine 60, that gives us √3/2. And we can see here that's going to be positive √3/2 because this is where y is a positive. So in this case, we can say that the point B is -1/2 and √3/2. So again, we can see here that the x-coordinate of B related to the cosine function. So it wasn't 1/2, it was -1/2, but it had the same magnitude as the cosine of 60. It just happened to be negative. So it still relates to the cosine of the acute angle in between the point and the x-axis. So let's just see now, though, what the cosine of 120 would be. So cos 120 gives us -1/2. So like question 1, the cosine of the angle measured from the positive x-axis anti-clockwise until we get to the line OB actually gives us the x-coordinate of the point. And in the same way, if we try the sine of the angle measured anti-clockwise from the positive x-axis through to the line OB, sine 120, that again gives us the exact y-coordinate of this point. So cos is seeming to us to relate to the x-coordinate of the point, and sine is seeming to relate to the y-coordinate of the point as well. Let's have a look at question 3. So similar idea, we've got a right-angled triangle, only here the angle measured from the positive x-axis around to the point of the line OB is 225. So with basic right-angled trigonometry, again like I've said before, we need an acute angle to work with. And so if this is 225, you can consider this as being 180 degrees plus an extra 45. In other words, this acute angle here will have a size of 45 degrees. So what we can do here is find the x-coordinate of B. So if we think about the cosine of 45, cos 45 will equal the adjacent side, which is from A to O, or from O to A if you prefer, divided by the hypotenuse, which once again is 1. So the point B for all of these warm-up questions has a distance of 1 away from the origin. So therefore, don't even need to rearrange this. OA is just cos 45. So you can try this on your calculators. You should agree with me here that cos 45 is root 2 over 2, which is the same as 1 over root 2. In the same way, sine 45 is going to be the opposite side, which is AB, divided by the hypotenuse, which again is 1. So therefore, AB is simply sine 45, which again is going to be root 2 over 2. Use your calculators to see that for yourself if you doubt it. So how does that relate to the coordinate B? Well, B is the x-coordinate of, x is the x-coordinate of B, I mean to say. And so we worked out the distance from A to O was root 2 over 2, but we can clearly see here B is where x is negative. So the magnitude of AO, or OA, is root 2 over 2, but because this is where x is negative, the x-coordinate will be minus root 2 over 2. And in exactly the same way for the y-coordinate, the magnitude of the y-coordinate will be root 2 over 2, but because here you can see that y is clearly negative, because this lies below the x-axis, the y-coordinate of B here will be minus root 2 over 2 in exactly the same way. So again, it seems that the cosine of the acute angle here relates to the x-coordinate of a point, same magnitude, different size, and the y-coordinate of this point here, B, seems to be exactly the same as the sine of the acute angle between the x-axis and the line OB. Same magnitude, that is, but different sign. So it seems that the magnitude is always the same, the sign might be different, but again, if we have a look at this angle measured from the positive x-axis anti-clockwise to the point of OB, we will also notice something here as well. So if I just did cos 225, again it gives us the exact correct x-coordinate, and if I were to do sine 225, it will give us the exact y-coordinate, which in this particular case, because the acute angle is 45 degrees, it's one and the same as the x-coordinate. And so it's seeming to build up a picture with this warm-up, but we can calculate the x-coordinate by just doing cos of this angle here, and the y-coordinate by taking the sine of this angle here, where the distance of B happens to be an exact unit. Finally, question 4 of a warm-up. Again, the angle measured from the positive x-axis, anti-clockwise around to the point on the line OB, is 330. So again, we can consider this angle here as being measured anti-clockwise from the positive x-axis. So in this case, I'm actually going to call this angle, generally speaking, theta, and see if we can postulate some results based on these warm-up questions from 1 to 4. However, let's just forget that for now and consider this as being like basic trig. This is a right-angled triangle. If this here is 330 degrees, and knowing that there's 360 degrees in a full circle, we can easily see that this angle here must be 30 degrees. We can now think about working out the x-coordinate of this point B by thinking about the cosine of this 30-degree angle. The cosine is the adjacent side, which is from O to A, divided by the hypotenuse, which once again is 1. So therefore OA is just simply cos 30, and you might remember what cos 30 was from question 1. If not, use your calculator. Cos 30 is root 3 over 2. So this point B, the x-coordinate of point B, will be root 3 over 2, because the x-coordinate here is on the positive side of the x-axis, so it'll be one and the same as what we've worked out here. The length of OA will be the same as the x-coordinate. we now need to think about the y-coordinate by considering sine 30. So the sine of the angle 30 will be the magnitude of the opposite side, which is the side AB, divided by the hypotenuse, which is 1. Therefore, AB will simply be sine 30, and sine 30 is 1/2. And so this side here is a half. So you can see, because B is below the x-axis, it's a half below the x-axis, therefore the y-coordinate of B isn't going to be positive a half, it will be negative 1/2. So again, we can see here, like we've seen for all of these warm-up questions, that the x-coordinate of any point 1 unit away from the origin relates directly to the x-coordinate made in this acute angled triangle, in this case 30. So it relates to this acute angle in the right angled triangle. For example, here, it's one and the same. The y-coordinate of any point 1 unit away from the origin relates to the sine function of this acute angle made in this right angled triangle. The magnitude is always the same, as we can see here, but sometimes the sign is different, but the magnitude is always the same. That's to say that the acute angle in this right angled triangle will always relate in the way that the cosine of this will relate directly to the x-coordinate, the sine of this will relate to the y-coordinate. But more than that, the main point to take away from this is each and every time, if we measure going anti-clockwise from the positive x-coordinate around to the line OB, then the cosine of the size of this angle will give the exact x-coordinate, correct magnitude and always the correct sign, and if we do the sine of this angle, it will always relate to the y-coordinate, same magnitude and also the same sign. And that is the key point which we're now going to explore further in the main part of this lesson. Based off the warm-up, we're now in a position to consider what we call the unit circle. It's a unit circle because, as you saw in the warm-up questions, we were considering the coordinates of points which are always 1 unit away from the origin. The locus of all points 1 unit away from the origin would be a circle of radius 1 centred upon the origin, and if it's got a radius of 1, hence that's why it's called the unit circle. So let's explore this idea further. So the definitions for sine, cosine and indeed the tangent can be extended to angles of any size using a diagram like the one below. So this is very similar to what we've seen for the warm-up questions 1, 2, 3 and 4. So it just so happens that, like I said earlier, the x-coordinate relates to the cos of this angle, and the y-coordinate relates to the sine of this angle here. So for a point P, x and y, on a unit circle such that OP makes angle theta with a positive x-axis, then cos theta equals x, that will give the x-coordinate of P, and sine theta, which is y, will give the y-coordinate of P. And so y is going to be this distance here, and x is this distance along. So we can actually define cos theta as the x-coordinate on the unit circle for any point P, and sine theta can be defined as the y-coordinate of P, where P is any point on the circumference of the unit circle. And more than that, we can even define tan as the gradient of the line from O to P. So tan theta is the gradient of OP, which is the change in y divided by the change in x. In other words, tan theta is y over x, which, like I've said, is the gradient of OP. So we can actually use these definitions to find the values of sine, cosine and tangent for any angle theta. So just because this is a circle, and a circle has 360 degrees, theta isn't limited to just between 0 and 360. It actually works for any angle theta. So for example, if we had 370 degrees, that would be one full loop plus an extra 10. And so the functions for 370 degrees would actually be the same as what the function values would give for an angle of 10 degrees. And just in terms of measuring this angle theta, it's very important to note that you always measure positive angles theta anti-clockwise from the positive x-axis. Negative angles, therefore, are measured clockwise from the positive x-axis. And so this is theta. An angle of minus theta would be measured down below. So negative theta would be looking something like this, and would be measured starting from the positive x-axis, going clockwise. And so this would be negative theta, like so. Now here's a little graphic illustrating how sine and cos can be defined. So here's the unit circle, and you can see here this green dot sweeping out an angle here, measured from the positive x-axis, going around in increasing size until it gets to 360, then it repeats. So this nicely explains why the period of cos theta and sine theta is 360 degrees. After a wavelength of 360 degrees, the waveform repeats indefinitely, again and again, to infinity. So this diagram might make your head spin. There's a lot going on here, but you can see here that as this angle sweeps out, the x-coordinate of this angle relates to sine theta, where this line here is 0, above is positive, below is negative, and this blue line here, as this angle sweeps out wider and wider, relates to the cosine of this orange angle, as it alternates from 0 through to 360, and then on and on. So it might be worth pausing the video at different points and just seeing this for yourself. You don't need to remember this diagram, but it's a nice illustration, albeit perhaps too complicated. But I thought it was worth chucking in here nonetheless. So there you go. Another thing to note with this diagram is you can see this circle's been split into 4 quarters. And these quarters are called quadrants, which I'm going to explain in a bit more depth here. So the xy plane on which the unit circle is drawn is divided into quadrants. So let's just talk about what these are. So first of all, the first quadrant. So we define the first quadrant as being in the top right hand corner, what I've highlighted here in yellow. So for the first quadrant, theta lies between 0 degrees and 90 degrees inclusive. The values of x and y are both positive, so the values of sine theta, cos theta, and tan theta are all positive. So for any angle theta in between 0 and 90, sine, cos, and tan are all positive. This then changes slightly as we move into the second quadrant. The second quadrant, we go anti-clockwise around. This corner here I've highlighted in green is the second one. In this quadrant, you can see that theta is more than 90, but less than 180. The value of x is negative, so because the value of x relates to cos theta is negative. Now y relates to the value of sine theta. Now y is still positive, as you can see. It's still above the x-axis. So the value of sine theta is positive. But tan theta, as well as cos theta, is negative. Remember, tan theta is defined as the gradient of this line OP. This line OP is sloping down, so tan theta is negative, as is cos theta, because x is negative. So in this quadrant here, the only trigonometric function which is positive is going to be sine theta. In the third quadrant, similar to the second, there's only one trigonometric ratio which is positive here. The third quadrant is this one in the bottom left. So it's going to go 1, 2, this is the third, the fourth quadrant we'll mention last. So in this third quadrant, theta is more than 180, but less than 270. Measuring clockwise in terms of a negative angle, we could say that this angle here it's less than minus 90, but less than minus 180. So going this way round, that's minus 90, and that's minus 180. For the sake of keeping it simple, let's just think about the positive values of theta. So it says here that the values of x and y are both negative. So tan theta is positive. Remember, tan theta is x divided by y, and negative divided by negative yields a positive. Another way you can think about that is, remember that tan theta is the gradient of this line OP. So we can see here that from P to O is going upwards. In other words, this line here, because it's going upwards, would have a positive gradient. But sine theta and cos theta are both negative. Remember that sine theta is the y-coordinate of P. The y-coordinate here is negative because it's below the x-axis. And cos theta relates to the x-coordinate of P. P here is in the negative portion of the x-axis, so it makes sense that cos theta again is negative. So the only one positive in the third quadrant is tan theta. Finally, the fourth quadrant, which is the one in the bottom right. So in the fourth quadrant, what we have is theta having an angle between 270 and 360. Beyond 360, we go up here and we're into the first quadrant again. So the values of x is positive and the value of y is negative. X is positive, x is cos theta, which is positive because P here is in the positive portion of the x-axis. But cos theta here, so cos theta is positive, sine theta, as you can see, will be negative because sine theta, which is the y-coordinate, as you can see, is below the x-axis. So the only thing here is cos theta, which is positive. Sine theta is negative because the y-coordinate is below the x-axis, and tan theta is also negative because the gradient of OP is negative. From O to P, the line is sloping downwards. So let's just run through those ideas again. So first of all, just to mention, like I said before, angles may lie outside the range from 0 to 360, but they will always lie in one of the four quadrants, because of the nature that sine, cos and tan repeat at least every 360 degrees. In fact, tan repeats every 180. So for example, an angle of 600 would be the same as 600 minus 360, which would be 240. So it would lie in the third quadrant. So 600 degrees, you could think about it as going one full lap of 360, then an extra 240 around the positive x-axis. So 240 would be in the third quadrant because it's more than 180 but less than 270. So the image below illustrates how to measure both positive and negative angles with respect to the x-axis. So here, these lines here going anti-clockwise, you can see goes and starts from 0, positive 90 if you go anti-clockwise, positive 180, positive 270, then back to 360, then we reset at 0 again. If we measure going clockwise, going this way here, then we start to measure angles in a negative fashion. So from 0 going a size of 90 degrees, that's actually negative 90. So an angle measured clockwise from the positive x-axis down to the y-axis of a magnitude of 90, that's measured as minus 90. Going half a circle clockwise is minus 180, 3/4 of a circle clockwise is minus 270, then a full circle going clockwise is minus 360, then it resets again to 0. Again, I'm going to show you a few graphs in this image below, and in green is going to be sine theta, red cos theta, and blue tan theta, between 0 and 360 for theta. So I'm going to put the four quadrants labelled as 1Q, 2Q, 3Q, 4Q for the first quadrant, second quadrant, third quadrant, and the fourth quadrant respectively. So here we are. So these graphs you will have seen before at GCSE, I've got no doubt. So the red is cos theta, green is sine theta, and tan theta is this weird one which sort of breaks off and goes back down again below. So tan theta, you probably remember, is a bit of a weird one. But anyway, I want you to just have a look at this and think about which ones you can see which are positive in the first quadrant. So on that point, having a look at this above graph here, we can use the quadrants to determine whether each of the trigonometric ratios is positive or negative, just by looking which of them are below the x-axis for each quadrant in turn. We could think about the negative ones as well, but just focus on the positives here. Which ones are positive in each quadrant? So first of all, just underline positive because we're looking at the positives. Think about the first quadrant first of all. So the first quadrant I just put in yellow here. We can see here in this quadrant, cos theta, the red line, is in the first quadrant throughout. So cos theta is always positive. Tan theta is all in this first quadrant. So tan theta is always positive in the first quadrant. And sine theta, the green line, again, is always in the first quadrant throughout. So that tells us that for the first quadrant, cosine, tan and sine, they're all positive. So for the first quadrant, all of the trigonometric functions are positive. Capital A for all. Let's now have a look and think about the second quadrant. I'm going to highlight this one in green. We can see here there's only one function which is positive in the second quadrant. Cos is all negative because it's below the x-axis, as is tan. The only one which is positive throughout the second quadrant is this green line, which is sine theta. So the second quadrant, sine only, is positive. Thinking about the third quadrant, which I'm going to put in blue, we can see here that only the blue line is positive in the third quadrant, which is tan. Sine and cosine, green and red respectively, are below the x-axis for the third quadrant. They're negative. The only function in the third quadrant which is positive is tan theta. So I'm just going to bring up T for tan to denote that this is the only positive one. So the third quadrant here, the only thing that's positive is the tan function. Finally, the fourth quadrant, I'm going to use this purple colour. The only one which is positive here is cos theta. That's the only line you can see in the fourth quadrant throughout. So if I just bring up the C for cos theta, it's clear to see that the only trig function in the fourth quadrant which is positive is cos theta. And this is well worth remembering. So A, S, T, C, well, starting from the fourth quadrant, reading anti-clockwise around, C, A, S, T spells cast. This diagram here is often therefore called a cast diagram. It's very useful, very powerful, and makes understanding which trig functions are positive and negative and where makes it really easy to remember. So just taking this diagram here again, C-A-S-T, cast, let's just make a few notes about this. So first of all, in the first quadrant, any angle theta in the first quadrant, sine, cos and tan are all positive. For the second quadrant, any angle theta in the second quadrant, only sine theta is positive. If theta was in the third quadrant, only tan theta is positive. And finally, in the fourth quadrant, only cos theta is positive there. Reading anti-clockwise from the first quadrant, we have a way of remembering the functions. So it goes A, S, T, C, which can be remembered as all silver toy cars. Another way you might want to remember it is that the letters spell cast when read anti-clockwise starting from the fourth quadrant. Like I've said before, for this reason, this thing here is often called a cast diagram. You can use the cast diagram to find sin, cos or tan for any positive or indeed negative angle using the corresponding acute angle made with the x-axis. So it looks something like this. So there's a cast diagram with the acute angle theta measured from the x-axis going upwards or downwards respectively. So although there's 4 different thetas measured here, the magnitudes of each theta are exactly the same with respect from being measured from the x-axis to the line going either up or down. From this as well, we can also generate some trigonometric identities from this cast diagram to its left. So as we've said before, theta is measured with respect from the positive x-axis going anti-clockwise. And so this is theta going further. That's almost 180, but less theta. So this one here is 180 minus theta. That's 180 plus theta here. And going anti-clockwise from the x-axis all the way around, this one here would be 360 minus theta. So it's always measuring anti-clockwise from the x-axis. So first of all, let's just think about different sine theta identities. And so sine theta is the y coordinate of any point along here. So we can see here, sine theta here will be the same as sine 180 minus theta, because this angle here is the same magnitude as this one, and both are above the x-axis, so both will be positive. So sine theta is going to be the same as sine of 180 minus theta. Okay, and we can think about this by just taking a point on the line like so. Okay, and so the y coordinate here is sine theta. And you can see here, over here, that this would be sine of theta, which also measured from the positive x-axis going anti-clockwise is the same as sine of 180 minus theta. Now, this one here, thinking like this angle, at this point here in red, that's going to be 180 plus theta. So, if we think about sine of 180 plus theta, and using the symmetry of this cast diagram, sine of 180 plus theta will have the same magnitude as sine theta. But think about where this point is in relation to the x-axis. The magnitude of sine of 180 plus theta will be the same as sine theta over here, because, to put it simply, the length of this line is the same as the length of this line. Only this one here, because it's below the x-axis, this will be negative. So in other words, sine theta is the same as minus sine of 180 plus theta. In a similar way, this one over here, again, it's below the x-axis, and so the sine of 360 minus theta will be minus sine theta. Or, putting it a different way, sine theta is the same as minus sine of 360 minus theta. If this confuses you at first, that's to be expected. By the end of this chapter, you'll be absolutely fine with this. If in doubt, just try a value of theta on your calculator. For example, try 30. You'll see that sine 30 equals sine 150, sine 30 is negative sine 210, sine 30 is negative sine 330, and so on. So let's think about cos now. So I'll clear that off, and now we can think about identities involving cos theta. Now cos theta relates to the x-coordinate of any point on the cast diagram. And so if I just take here and label these points in blue, like so, then cos theta will be the x-coordinate of this point, which I'm going to just show by just doing a blue line along here. So that's going to be cos theta, this dotted blue line. So cos theta, first of all, if I compare it to cos of 180 minus theta, which is this one here, it will actually not quite be the same. We can see here that this length, which represents cos theta, will actually be one and the same as this length over here. I'll put it in a different colour just to differentiate the two. I'll put this in a green colour perhaps. So these have got the same lengths, and so cos theta will have the same magnitude as cos of 180 minus theta. But because here the x-coordinate is negative rather than being positive, it will have the same value as cos theta but multiplied by minus 1. In other words, cos theta is the same as minus cos of 180 minus theta. In the same way, when we've got cos of 180 plus theta, this point here, which has an angle of 180 plus theta, measured anti-clockwise from the positive x-axis, we can see here that this point would also have a negative x-coordinate. For that reason, cos 180 plus theta will be negative. And finally, in the fourth quadrant, for this point here, you can see that cos of 360 minus theta will have a positive value as well, because here, this point is on the positive portion of the x-axis. So cos theta equals cos of 360 minus theta. Tan theta is the last one we're going to consider. So if I just clear off all of these now and use a different colour so we don't get too confused. Tan theta, just remember, tan theta is the gradient of any line from the origin through to any point. So if we just think about the 4 different points in each of the 4 quadrants. So tan theta here is positive in the first quadrant. Remembering, in the first quadrant, sine, cos and tan are all positive. In the second quadrant, tan of 180 minus theta, let's just think about this one. This one here, from this point to the origin, that's going downwards, so that's got a negative gradient. So we just pop in a minus sign here. In the third quadrant, which is listed as t, that's because tan is going to be positive. So tan of 180 plus theta is positive here, and so it's going to be the same as tan theta, because from this point to the origin it's going upwards, as the line is in the first quadrant. So think about it, the first and third quadrant form part of a bigger line which has a positive gradient. The second and fourth quadrants, the even quadrants, are going to have a value of tan being negative, because this makes a line sloping downwards. So the fourth quadrant will also be negative for tan. So tan of 360 minus theta will also be negative. So the way I'd think about it would be like this. All we need to do is think about where the point would be on the cast diagram based on the angle in question. We then draw an X shape, label on the same magnitude angle for each quadrant, and then we just consider that whatever quadrant it happens to be in, whether it be the first, second, third or fourth, we can write it down in terms of one being equal to the other, and then we just consider if it's a minus sign or a positive sign. Whether a function is positive or negative, that's where the cast diagram comes in. In the first quadrant, sine, cos, tan, all positive. In the second quadrant, only sine's positive. In the third, only tan. And last but not least, in the fourth quadrant, only the cosine function will be positive. You might be thinking that was very heavy in terms of explanation and conceptual understanding and reasoning, but I promise you, when we apply these ideas, it's actually very simple indeed. So on that note, before you start some questions on your own, here's just some worked examples using the cast diagram and the graphs of the trig functions to find acute angles. So just question 1 here. Express the following in terms of trig ratios of acute angles. First of all, sine of minus 110 degrees. This angle's negative, and so we're going to be measuring it from below the positive x-axis. So we're going to be measuring this way. That's minus 90, minus 100, minus 110. So we're going to have a line from the origin going about here. So here's one I drew earlier, which is a bit neater. As well as this, just remember the cast diagram in terms of labelling on cosine, all, sine and tan. And like I said earlier, this is an angle of minus 110 degrees. You don't need to be particularly accurate, but you do need to know to get it into the correct quadrant. And so I've put a dot here to denote that this is the quadrant we're interested in. What we need to do, always, once you've drawn the angle on, you need to find the acute angle between this line and the x-axis. So if this has got a size of 110 degrees, its actual value is minus 110, but its size is 110, this angle here will have to be 70, and this is our key angle. So we need to label this in like so. Then with a cast diagram, I also think it's a good idea, just to make it easier, just to extend the diagram and do an X centered on the origin, so that each of these acute angles measured relative to the x-axis are repeated 4 times here, 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 and here, like so. However, the only one we're interested in here is this one here, where only tan is positive, because in this quadrant here, only tan is positive. So we've done the hard work now. So what we can say here is that sine of minus 110 will relate in some way to sine of 70. Either it's going to be exactly the same as each other, or this might have a minus sign in front of it. So in terms of deciding if it's got a minus sign or not, all we need to do is to consider the quadrant it's in. If it were in the all quadrant or the S for sine quadrant, that would remain positive. But in the T quadrant, only tan is positive, therefore sine of 70 is going to actually be minus. In other words, sine of minus 110 is negative sine 70. Sine 70 has a positive value. This one here is in a quadrant where only T is positive. So we need to put a minus in front of that one. So what you can also do here, if you remember the graphs well enough from GCSE of sine, cos and tan, you can actually use the graph to help you. So using this graph here of sine theta, you need to first of all know that it has to relate to 70 degrees. So minus 110, we can use the graph and just sketch in roughly where minus 110 would be. So it'd be about here. And you can now use the symmetry to help you out. So minus 110 is obviously 20 degrees in terms of how I picture it from the trough at minus 90. So using the symmetry of the curve, we'll also be looking for a bit here, which is 20 degrees away from the peak. So 20 degrees away from 90 will be here, which will be where sine is 70. But of course this point here is a reflection in the x-axis of this point below. So in other words, sine 70 is negative sine of minus 110. Or written in this form here, just multiply both sides by minus 1. In other words, we can say that sine minus 110, making this one the subject, is minus sine 70. Again, just by multiplying both sides by negative 1. As useful as the graph of sine, cos and tan are, it's best to move into thinking and using the cast diagram as soon as possible, because with enough practice, this makes things very easy. It might be confusing at first, but do stick with it. This will save you a lot of hassle in the future. Part B. You want to consider now cos of 260 degrees. So cos 260 will be somewhere like this. This is 90, that's 180, not quite 270. It'll be somewhere, again, in the third quadrant. So we're going to be looking at a point down here somewhere in the third quadrant. Again, because it's a cast diagram, what we need to do first and foremost is label on cast correctly. So get the cast diagram labelled CAST, then draw on a point which is 260 degrees measured anti-clockwise from the positive x-axis. So it's going to be somewhere in this quadrant. I've done the point down here. So again, it's in the third quadrant where only t is positive. So we need to now think about what the acute angle is with respect to this line and the x-axis. If this is 260 degrees, we can think of this angle as 180 plus an extra 80. In other words, this acute angle here must be 80, which we can label on, and then, just for the sake of keeping it simple, do a big X centered on the origin, so this 80 degree angle is repeated in all four quadrants like so. So cos 260, because we've got this acute angle of 80 identified, this will link and relate to cos of 80 degrees. We know that for sure because the acute angle is 80 degrees. The only question now is if this is positive cos 80 or negative cos 80. In other words, this cosine function, all we need to think about, is it going to be a positive or negative in this quadrant? Because it's in the tan quadrant, only tan is a positive function down here. Sine and cos, therefore, are both negative. And so this cosine function here has to have a negative value. Sin, cos, tan of any acute angle is always positive. So to make this negative, we just need to bang a minus sign in front of it, and then we're sorted. Again, if you'd prefer, you can use the graph of cos theta. So here it is. So we'll have a look at whereabouts 260 is. If that's 180, and that's 270. 260 is about here. Now, each person pictures it in a different way. The way I'm picturing this is, how far away is it from an x-axis intercept? It's 10 degrees away. So where's an acute angle where we're 10 degrees away from an intercept? It'd have to be here, which should be 80. And so this point here will have the same magnitude as this point down here. Only this one's clearly positive. What we need, though, is for it to be negative. And so we take cos 80 and multiply it by minus 1, hence sticking this minus sign in front of it. Finally, part C, tan 190. It's a cast diagram, so let's get the cast labelled incorrectly. Tan 190, again we measure going anti-clockwise from the x-axis, 90, 180, 190, it'll be somewhere here perhaps. So it's going to be in the third quadrant labelled T. So here's one drawn on a bit nicer than this one, like so. And so the quadrant we're interested in is the third quadrant where tan is positive. If this is 190, that can be considered as 180 plus an extra 10. In other words, this acute angle must be 10 degrees. So label this on, and then extend it so that this 10 degree angle is repeated across all four quadrants. Just a good habit to get into. And so down here in this quadrant, tan 190 is going to relate to tan of 10 degrees in some way or other. The only question is the tan function in this quadrant we've identified it as being in, is it going to be a positive value or a negative value? Well, in the third quadrant of the cast diagram, it's labelled T, which denotes that tan is always going to yield a positive value in this quadrant. Therefore, tan 190 must be positive and must relate to tan of 10. 10, an acute angle of tan, or sine of, or cos of course, will always be positive. So because tan 10 is already positive, we don't need to put any positive or negative sign in there. So in other words, that statement is correct as it reads here. Once again, you could verify this using a graph of the tan function, like so. Tan 190 is about here. 10 degrees to the right of an x-axis intercept. 10 degrees right from 0 is 10. And as you can see, that will give a same value of y, where y is tan theta. I would say, again, to move away from using the graphs. If you really want to use a graph, you can, but the cast diagram will save you much more time in the long run. So it's now over to you to have some much needed practice on this. With enough practice, it becomes quite simple, in fact. So the exercises I'm suggesting for you are on page 207, exercise 10a in the book. So questions 1a through to e, question 2, question 3a to e, 4a to e, 5 and 6. Do them all and make sure you've got them all correct. If you've not got them correct, check your answers and ask me if you're struggling. You need to master this skill. It's a really important one. Thanks for listening to the video. Remember to subscribe please if you can, and I'll see you soon in the lesson or in Achieve or even on an email. Keep in touch, keep working hard. I'll see you all soon.